Today topic is Paternò-Büchi reaction. So I think I have covered everything on photochemistry except Paternò-Büchi reaction and the Barton's reaction. So those two today I am going to do. So Paternò-Büchi reaction is example for photocyclization reaction. So this is example for 2 pi cyclization reaction. Okay, so here we have a carbonyl compound plus olefin. Upon we will irradiate lambda max of carbonyl compound. So now there is a formation of a mechanism I will explain later. There is a formation of oxetane. So this is the product we will get in a Paternò-Büchi reaction. And now there are two excited states are possible here, N2 pi star singlet as well as N2 pi star triplet. Just remember always N2 pi star singlet means always singlet excited state is stereospecific, and this is the non-stereospecific. So why singlet is stereospecific? Because as we know that singlet and triplet, singlet will be higher in energy and the lifetime of singlet is very less, and triplet is lower in energy, the lifetime will be more. So imagine the lifetime of singlet state is 10 seconds and the lifetime of triplet will be 20 seconds. Now by that time there is a spin inversion, imagine this is a singlet state, it is like this, and for olefin it's like this. If it is the N2 pi star singlet, so only 10 seconds is left. Within that 10 seconds these two form a bond and these two form a bond. So imagine this methyl groups are here. Now if it is a triplet excited state, and there is a chance that this will undergo ring inversion, this will be, I think this will be down, imagine this is down, and here two possibilities will become this will be one possibility, and another possibility is a spin inversion. So this will come down, this will come up. So here we will get a two products. This will be one product plus this will be another product. So in case of when we have a N2 pi star triplet, this is a non-stereospecific. Here you will get a mixture of products because of the lifetime of triplet state is more, because of that this spin inversion will takes place. Whereas when we have N2 pi star singlet, in that case lifetime is very less, so spin inversion will not takes place, so stereospecific reaction. Okay, next. So Paternò-Büchi reaction means what? Reaction of carbonyl compound plus olefin gives oxetane. So here the alkyne, with alkyne also Paternò-Büchi reaction is possible. R plus, here we have alkyne, this come this way and this goes this way. R. Now so this is called oxetine and this is called oxetane. This is oxetane, this is oxetine. So when we have a olefin, so that time we'll get a oxetine, but when we have a alkyne, that time ring opening will takes place. This will comes like this and this goes like this, so we'll get a alpha beta unsaturated carbonyl compounds. Because so this is a strain free, but here we have sp2 carbon, so because of that reason, so this is having a strain. Compared to this is having a lesser strain. Okay, that's why when we have alkyne, then in that case ring opening will takes place, because oxygen is highly strained molecule. So alpha beta unsaturated carbonyl compound will be the major products. So can we call Paternò-Büchi reaction as a regioselective reaction? Yes, we can call it as a regioselective reaction. So here we have benzophenone plus one unsymmetric olefin. So here two products are possible, pH and methyl plus pH, this is the methyl. So this is major and this is minor. Okay, so we can call it as a regioselective reaction. So because when we have unsymmetric olefin, so that time we are getting two products, and one is in the major product and another one will be the minor product. So why this is major, why this is a minor? See, so this carbonyl carbon is electron deficient, right? So just remember, electron deficient carbon has to form a bond with the electron rich carbon. So that is the main concept here. So this is electron deficient, so it has to form a bond with electron rich carbon. So here two carbons are there, this carbon and this carbon. So which is having more electron density? So this carbon, because plus I effect of methyl group. That's why this bond forms first. Okay, so where we have a this carbonyl carbon and this carbon bond, so that is major. So here we have this one, so this is major. So that's why we call Paternò-Büchi reaction as a regioselective reactions. And we'll see the pathway, how the reaction goes. So initially we have carbonyl compound as well as olefin, and we'll give a lambda max of carbonyl compound, and this goes from the single state to ground state to S1 state, and then through intersystem crossing it goes to triplet state. At this triplet state there is a it's possible there is a formation of Exciplex complex, or we also call this one as a temporary charge transfer complex, That means there is a existing of this kind of structure. Some interactions will be there between these two. So this complex is called as Exciplex complex, and at this stage the electron will transfer from the olefin to, sometimes olefin to carbonyl compound, sometimes carbonyl compound to olefin. So there are two possibilities. I will explain those possibilities now. And after formation of Exciplex complex, there is a formation of a bond and it's a generation of 1,4 biradical, and finally we have a oxygen complex. Okay, so now there are two possibilities we have. We can have a carbonyl compound plus olefin which is having a electron releasing group. This is one possibility. So another possibility is olefin and carbonyl compound and olefin which is having electron withdrawing groups. In the first case olefin is electron rich. In the second case olefin is electron deficient. And here the olefin act as a donor and carbonyl compound act as a acceptor. In the second case, where we have olefin with electron withdrawing group, this act as acceptor and olefin act as a donor. Okay, so which one is having more electron density, so that act as a donor, and which one is having less electron density, that act as a acceptor. If olefin is having electron releasing group, so that means that is donor, and if olefin is having electron withdrawing group, that means that is a acceptor, that act as acceptors. Now, okay, carbonyl compound plus electron releasing group. Similarly, carbonyl compound plus electron withdrawing group. Now, so here uh, first there is a formation of oxygen and carbon bond, and we generate this kind of radical, and in this case electron withdrawing group, in this case we are having this kind of 1,4 bi radical. Okay, when olefin is electron rich, that time CO bond is forming first. When olefin is electron deficient, in that case CC bond is forming first. So if we see the MOT diagram, like for carbonyl and olefin, so this is for carbonyl. We know that carbonyl and olefin, this act as a photosensitization. I have made a video on photosensitization, you can go for it. So this act as a photosensitizer. Okay, so here in this reaction we are taking a lambda max of carbonyl group, right? That means that will be a donor and this will be acceptor. So if when we are taking this h nu of lambda max of carbonyl compound, so this goes to the excited state. Excited state means higher energy. So this for the carbonyl compound, and this will be the olefin, because we are taking the lambda max of carbonyl compound. That means carbonyl compound only goes to the excited state, and this will be in the ground state only. So the ground state will be less energy. That's why this is for olefin, this is for olefin, and this is for carbonyl compound, and this is n orbital, and this is the pi star orbital. Since carbonyl compound is in excited state, the 2 electrons will be distributed like this: 1 electron in n orbital, 1 electron in the pi star orbitals. Okay, similarly, and because olefin is a ground state, both the electrons are present in the pi orbitals, and this is pi and this is the pi star. Okay, so in the first case, so this is donor and this is acceptor, right? So donor means this give electron from pi orbital, so this electron, so now this is donor and this is acceptor. Don't bring that photosensitization concept here, that will be different. Just see here pi orbital is here and n orbital is here. So here this is donor and this is acceptor. So which orbital is very close to pi here? N orbital. That means it gives electrons to n orbital. So there is a formation of, if the electron is going from the pi orbital to n orbital, then there is a formation of CO bond. If the electrons are going from the pi star to the pi star of carbon, pi star of carbonyl to pi star of carbon, there is a CC bond formation takes place. Okay, so this is for this first reaction, and for the second reaction we'll see MOT. So now here we have an excited state. This is in excited state n pi star, and this will be in the ground state pi star. This is for olefin and this is for carbonyl group. Here 2 electrons are here. Now this pi star orbital is close to which orbital? So this pi star orbital is close to the pi star of CO. This is for CO and this is for this olefin. Because of that reason, here the electron will transfer from the pi star orbital of carbonyl carbon to pi star orbital of olefin. So pi star orbital means corresponding to this, n orbital means this. Okay, so because of electron is transferring from the pi star orbital of carbon to pi star orbital of carbonyl sorry, because the electron is transferring from the pi star orbital of carbonyl group to the pi star orbital of olefin. Because of that reason, the first CC bond formation will takes place, and the second this bond formation will takes place. And when olefin is electron rich, in that case first CO bond formation takes place, followed by CC bond formation. So this is the mechanism when we have two different olefins, I mean electron rich and electron efficient. So we have two types of carbonyl compounds here. So I am not going into the detail, I am just explaining like that. So we have aliphatic carbonyl compounds and aromatic carbonyl compounds. Okay, so these two are here. When we have a aliphatic carbonyl compounds, in those cases N2 pi star singlet will be the excited state. When we have N2 pi star aromatic carbonyl group, in that case the excited state will be the N2 pi star triplet. So I have explained before why singlet state is stereospecific, triplet is non-stereospecific. So whenever we have a aliphatic carbonyl group plus any olefin, this is stereospecific reaction. So whenever we have a aromatic carbonyl compound, that is non-stereospecific reaction. So here right. So here we have acetone plus olefin. So this is the having a cis geometry, lambda max cis geometry, and the product side also will be a cis geometry. Okay, then here we have a trans geometry, and in the product side also trans. So this is the stereospecific. So when we have a aromatic carbonyl compounds, here these are non-stereospecific. So here we have a cis geometry, but here we'll get a cis product as well as trans product. Because I have explained already, there is a spin inversion CC bond rotation will takes place here. CC bond rotation will takes place, because of that spin exchange also takes place. So that is the reason why N2 pi star triplet is non-stereospecific. And some of the examples I have for Paternò Büchi reaction here. And we have benzophenone plus alkyne, and which forms a oxytene. When when we have a alkyne, in that case we know that alpha beta unsaturated carbonyl compounds forms. This comes like this, and this goes here. So this will be the product. And then here also this carbonyl group and this olefin undergoes reaction, okay, and now the ring opening will take place. This bond comes like this, this bond goes like this, here no change, and here it will be a double bond COPH, and I think here a pH comes. So this is the product. And some intramolecular Paternò-Büchi reactions. This in photochemistry mostly the intramolecular reactions are very important. So when we have alpha beta unsaturated carboxylic acids, okay, so this bond comes like this, this comes like this. This is also 2+2 cyclization reaction. You will get here 2 phenyls and second place 1 phenyl, and here OH. So this is the enol form. So enol form is not stable, so 1,3 hydrogen migration takes place, sorry, 1,2 hydrogen shift takes place, so we'll get a carbonyl compound. And this is also an example for intramolecular cyclization reactions. And here this is the product. I'm just writing directly product because I have explained already the mechanism, so we just go through it. Then here we can take naphthyl group, oxygen, this one CC naphthyl. Okay, these are some examples for a Paternò-Büchi reaction, and there are some limitations. There are 2 limitations we have. These 2 limitations are also very important. So the first limitation is whenever we have energy of triplet state of carbonyl compound is greater than energy of triplet state of olefin. So here I have explained about the photosensitization, so you just go through it. So whenever the energy of carbonyl compound is greater than olefin, in that case the photosensitization will come into the picture. So there the percentage of Paternò-Büchi product will decreases. Okay, instead of Paternò-Büchi reaction, here cyclic adducts will, sorry, dimers will form. See, we have this Narbonne system. Okay, this is having energy of 72 kilocalories. So when we treat with benzophenone, which is having energy of 69, so here the energy of energy of olefin is greater than the carbonyl compound. So this is not following this condition. In this case Paternò-Büchi reaction only we will get. Okay, pH and pH. And when we have a, instead of phenyl, if we replace one methyl group, this is having an energy of 74 kilocalories. Now the energy of this carbonyl compound is greater than the energy of olefin. So because of that reason, here we'll get a dimers. And this is in the reverse form. These are the 2 products here we'll get. And similarly, when we have a acetone in acetone also we'll get a mixture of means dimers. So this is the one condition. The another condition is like in the triplet state, when we have a triplet state, in the triplet state, this is upon treatment with the olefin. Here we get two product, oxetine, this is having 64 percentage plus photo reduction product will be 36 percentage. So I will be making a separate video on photo reduction, so there I will explain what is the mechanism for photo reduction. So as of now we just remember only these two limitations. So when the energy of carbonyl compound is greater than energy of olefin, in that case dimers will form because of the photosensitization. And this is also remember when olefin is at a triplet state, it's mostly like oxetine only the major product, but photo reduction also will takes place. So this is about the Paternò-Büchi reaction. I hope everything is clear. If you have any doubts about this Paternò-Büchi reaction, so you can comment in the comment box. Thank you.